welcome to the second session of the day, and I hope you can survive another 1 hour and a half without coffee, or maybe you already had coffee, but we are a little bit over time, so I will keep introductions clear. This session is dedicated to a specific ManyAnalysts project in ecology and evolution, so we will go more into the details of a single project. And we have 3 speakers, and they will give 20 minutes presentation each, and the time for questions will be after. So please remember or write down your questions for each of the speakers. And this is because they speak essentially about the same project. And it's very exciting to have here Hannah, Elliot, and Tim. And Hannah is a postdoctoral researcher from University of Melbourne. Elliot is a PhD student from University of Melbourne, and Tim Parker is a professor from Whitman College in the USA. So this start. And we should be able to find the slides here. Okay.
Thanks so much. It's really exciting to be here with you today and to talk about a project that is really close to my heart, sort of possibly the favorite thing I've ever done, despite the unfortunate difficulties that we hit along the way, which I'll tell you a little bit about, and I'm sure the others will also zoom in on a little bit too. So I'm going to have to skip over a few slides because Colin gave us such a fantastic introduction to this topic. So bear with me as I ad-lib this a little bit. So we did a ManyAnalysts study for ecology and evolution. So I'm going to give you a bit of a background on the specifics of an ecology and evolutionary context and why and how that relates with the idea of a ManyAnalysts project. So there's a lot of heterogeneity in ecology and evolutionary biology, and there's a few different sources of this. Meta-analyses. Meta-analyses in ecology, which are looking at studies that have asked similar questions, find that there's substantial variation in the results. This particular example looked at 86 published meta-analyses, and they found that the I-squared value, which is the proportion of variance between studies, had a median of almost 85% and a mean of almost 92%, which they're really big numbers. I probably don't need to tell you that. And there's 3 main sources of heterogeneity in ecology and evolution. I think this is probably true in other systems as well, though they might call them slightly different things. And they all contribute to this high I-squared value that you're getting in these meta-analyses. The first one is biological heterogeneity. The results of ecology and evolutionary studies depend inherently on the environment. This is maybe more true than in other fields because you're going out in nature and studying things in situ where they're affected by all sorts of environmental variables that we're aware of and also ones that we're not really aware of. So the obvious things like wind, rain, climate, time of day, time of year, but then there's also stuff that you just don't notice. So even if you have 2 sites where you think that it looks pretty similar, they might be responding differently because of, I don't know, historic land use that you're not aware of, or their context within a greater landscape that you're not thinking is relevant. As I was saying, seasons are a really strong driver in these systems as well. Obviously, spring, when everything is reproducing and going nuts, is going to be very different to winter or summer. Typically, when ecologists and evolutionary biologists are looking at how the results compare to the literature, this is what they're thinking about. They're trying to work out how their system is different from the systems that other people have studied and how that will be driving the difference in their results. Which completely overlooks the idea of the methodological and analytic heterogeneity. People sort of tend to let these fade into the background and assume that they're not really affecting what results people are finding. So we have methodological heterogeneity. That's about how data is collected and study designed. So study designs vary a lot in spatial and temporal scale. One study might look at changes at the scale of a single block of vegetation, another might look at samples across the whole state or the whole country or the whole world. And that's going to be you wouldn't expect necessarily the same results from those things, even if the question is very similar. One study might collect data on the same population of animals over 5 years, and another study might collect data on 5 times as many animals over one single year. And again, you'd expect the information you get from those studies to be different. Data collection methods are also really important in driving variation between studies. So you might use different tools or collect different variables for the same thing, like you might measure size as weight or length or height. NutNet is an interesting example. So there's a few different distributed network experiments in ecology and evolution, and NutNet is an example of these, which is very much a big team science thing, but from a non-meta research perspective. Though I would say that a lot of their results could be just slightly reframed, and they're basically meta research unintentionally. So NutNet, they're studying grassland sites around the world and how nutrient input impacts the way the species grow. And they use standardized methods across all of the sites, and they're pretty strict about exactly what you have to do and exactly what tools you use and when you sample and things, which is supposed to limit the influence of methodological heterogeneity. So there's obviously still going to be some slippage depending on, because following those rules are obviously never going to be quite as straightforward as you expect. Then there's analytic heterogeneity, which is what we're interested here in the ManyAnalysts project. So different researchers make different analytic choices, and these choices lead to different statistical outcomes. Andrew Gellman calls this the garden of forking paths, where you're making a whole lot of analytic decisions as you're doing an analysis, and depending on which of those different decision pathways you go down, you might end up somewhere completely different. As Colin was saying, there's growing evidence that this impacts the results of our studies, and we wanted to see how this related in ecology and evolution context. I'm going to skip over this section on other ManyAnalysts projects. This is the original 29 analysis teams. And here's the results here. You can see that some are finding their confidence intervals are overlapping 0. And there are a couple of these outliers, which I think they found were explained by using unusual methods, which has driven subsequent studies to include a review component so that they can identify which of the analyses are high quality and which aren't. Because it's obviously really easy to post hoc work out that those are bad analyses, but if you didn't know that they're outliers, you mightn't have thought that they were going to be bad. Here's that Fresnel study, and you can see that their results are varying between negative to a positive effect, with most people finding no effect. And so the one from microeconomics, a similar kind of pattern is going on there. So I wanted to relate this back to some work we did in the past on questionable research practices, specifically cherry picking, because I think that's really relevant in this ManyAnalysts space. So here is a table describing some results from a study we did a while ago and comparing them to rates in other fields. So these questionable research practices, and the rate is how many people have done each of these practices at least once. I'm going to just zoom in on the cherry picking here, where we're talking about omitting non-significant variables or studies from your paper, omitting non-significant covariates, and omitting analyses. And you can see that we're looking at rates of between 40 and 65%, which is pretty on par with other fields, a little bit higher than criminology and psychology in some instances. So cherry picking is selectively reporting parts of the study that show statistically significant or otherwise exciting and appealing results. And it's questionable because it increases the chances that you're reporting something that's not truly indicative of a biological or interesting effect. And it makes your research look more certain than would be warranted if you included all of the dead ends in your paper. I think that the 40 to 60% of ecologists having done this at least once is a massive underestimate. Some of you have heard me say this before. Because a lot of us are collecting data like this. This is my one sheet from my master's. So obviously I'm equally to blame as everybody else. You can see that I've collected 30 variables on this spreadsheet. And there was also 112 different bird species that were recorded. And I could choose to transform any of these variables in any way that seemed sensible to me, and also include any environmental variables on climate or soil or solar irradiation from the internet that I think might be interesting, that I could just add to at any time that I wanted. And then work out your analysis after you've collected the data. And there are just so many options, and you want to understand everything. So you can ask the question in 1,000 different ways and look at it 1,000 times. And in the end, you find something that you think's the answer because you've looked at it all. It's hard to know how much of that's just driven by you found something that's significant. So I think it happens really unintentionally. And then by the end, you've done so many different analyses that you couldn't possibly fit them into a paper in any kind of logical way, or with any kind of word limits. So if you're doing best practice, everything ends up in the supplementary that nobody ever looks at, or more likely you leave a whole bunch of stuff out because it seems irrelevant by the time you get to the end. So yeah, I think cherry picking is a very big problem in ecology and evolution. So it makes a lot of sense how we get there, and it's not at all for any kind of malice. It's just from this desire to understand exactly what's going on. So does it matter if we're analyzing things differently in this kind of context? And that's what we wanted to look at here in the EcoEvo analysts project. So we started off in March 2020, where we were provisionally accepted as a registered report by BMC Biology. This is hopefully going to stop us from falling into that exact problem with cherry picking. Because I'm going to tell you in a minute about how many different variables we collected on this as well. In April 2020, we began recruiting researchers on Twitter and via listservs, and we invited researchers to either analyze one or both of two different data sets or questions, and or sign up to review other people's analyses. And the response from the ecology and evolutionary biology community was so much better than I could have ever imagined. I remember before we sent out any people recruiting who were like, look, if we get less than 10, I'm not sure this is going to be a goer. That was not an issue. So we thought a lot about the types of questions we wanted to answer. Even previous ManyAnalysts studies, they're reasonably tight, conscribed questions. But that's not really how things roll in ecology and evolution. You sort of start with a reasonably vague research question, and then you have to work out exactly what that means. And usually that happens after you've got the data. So we wanted to sort of incorporate that process within this as well. So it's going to introduce more variation here. So question one we're looking at is, to what extent is the growth of nestling blue tits influenced by competition with seedlings? So we have two different measures that could be used for growth, which is chick weight and tarsus length, from a whole lot of broods, some of which were part of a brood size manipulation experiment in the UK. And we've also got variables on the parentage, the nest location, the clutch and brood size, chick sex, chick survival, and measurer ID. And 79 teams submitted analyses of this question, and there was 132 usable effect sizes. Question two was, how does grass cover influence eucalyptus seedling recruitment? And we had 4 different variables that you could combine in a variety of different ways to work out what grass cover might mean to you. And then there was also 3 different variables that describe eucalyptus seedling counts. So that was different sized seedlings, and people could choose whether they wanted to include all of those seedlings or only some of them. And then there was 30 other variables from 350 odd sites across Victoria in regenerating farmland. So these variables included the identity, coordinates, aspect, which is sort of which way it's facing, season, ground cover categories, precipitation, solar radiation, and soil variables. We had 68 teams submitting a total of 80 usable effect sizes for this question. So I'm sure I will have forgotten some of the variables we collected, but as a starting point, we asked people to fill in these online surveys to try and collect all of the information we might need. It was not all of the information we needed. That was rectified over time. And we also asked for information about them. So their level of education, familiarity with statistics and other variables about the analysts. And then information about the analyses themselves. So what answer they expected to the research question, which predictor and response variables used, their methods, which we asked them to describe as if you were writing it up for an article, and also provide their analysis code, their results written up as if they're writing a journal article, as well as specifically calculated effect sizes and model predictions for a couple of different pre-specified scenarios. And then we wanted them to describe what answer they felt they'd found to the overall research question. And for reviewers, we're aiming to have all analyses reviewed by 5 reviewers. I think we fell short on a couple of analyses, but we're pretty close. And we wanted to know whether the quality of the analysis explained variation in results, because that's one of the main concerns that was drawn up by that original Silverzahn paper. And we got reviewers to give a numeric score for each analysis, as well as a subjective rating of the review, as you might do in a formal peer review setting. So deeply flawed and unpublishable, major revisions, minor revisions, and then publishable as is. And then we got them to explain their rating and evaluate the decisions that each of the analysts have made. A lot of this stuff we haven't got to analysing yet, and we probably won't analyse in the first manuscript about this. Might be up to subsequent people or subsequent efforts of our own to really drill down into all of these things, because there's a lot that could be looked at. The pre-registered research questions, we've obviously statted these out into specific models in our paper, but I won't go into that detail here because it's not my level of expertise really, and a bit difficult to explain. The main 3 questions we wanted to answer were, how much do effect sizes and model predictions vary between analyses? And we looked at both a standardized effect size, and we asked people to calculate their model predictions in 3 different circumstances, because we thought that would work better with some of the different model types that aren't going to be represented well by effect sizes. And we wanted to know how much of the variation is explained by peer review ratings of the analyses, and how much is explained by the uniqueness of which variables they chose. Some things we didn't expect. Well, we had no idea there'd be such an amazing response from people. That's one of the things that makes this such an inspiring project to be part of. So many people got involved, and it was just fantastic. People also didn't just do one analysis, which is one of the things that really tripped us up, because, I mean, thinking it through, we should have expected people to do multiple analyses, because that's how everybody analyzes things, at least in ecology and evolution, but we didn't, so we had to collect more data afterwards. But it means we had a lot of analyses to compare, and it was really tricky. Very, very tricky. And making our analyses reproducible is also more complicated. And if anybody else has pre-registered something, I hope you didn't have this experience, though I think you possibly will have. Several of the analyses we pre-registered didn't make any sense at the end. When we got down to it, didn't make any sense at all. So we'll be explaining that in the final manuscript. All right, so that's it from me. I'm going to hand over to Elliot, who's going to take you through some of our preliminary results on this.
Thanks, Hannah. That was great. Hi, everyone. I'm Elliot, if you haven't met before. So I'll just go through a handful of the key results today, just because there are so very many of them. And just as a brief reminder, the main research question that we wanted to address was, to what extent does analytical heterogeneity drive variation in results? Well, ta-da. Here's a forest plot of both the blue tit and eucalyptus data sets, and I'll just drill down into that. So here's a forest plot of the effect sizes from the blue tit analyses, where each of the points represents an effect size from a single analysis, and those effect sizes have been transformed into standardized correlation coefficients, so we're not comparing apples and oranges. And these error bars here are the confidence intervals for those estimates. So the line at 0 represents the line of no effect, whereas results to the left of the 0 represent analyses that found sibling number and nesting growth to have no relationship. And effect sizes to the right of 0 indicate that the analysis found a negative correlation. So as sibling number increases, nesting growth decreases. And the magnitude of the effect size is given by that distance from 0. So the further away the point is from 0, the greater the strength of the effect found by the analysis. There is substantial variability in the direction of effects. So the majority of analyses of the blue tit data set found nestling growth decreases with sibling growth, with the average meta-analytic mean of 0.29. But a handful of analyses found there to be a positive correlation. There's also substantial variability in the direction of effects, with correlation uniformly ranging from about -0.4 to greater than 1. And as Hannah explained earlier, in meta-analysis, we can quantify the proportion of heterogeneity driven by between study variance to heterogeneity driven by within study variance or sampling error. So I-squared was extremely large, coming in at about 98%, showing that nearly all heterogeneity is driven by between study variation or analytic heterogeneity, with only about 2% of the total variation driven by sampling error. Moving on now to the eucalyptus analyses. This time to the left of the line of no effect. These analyses found there to be a negative relationship between grass cover and eucalyptus seedling success. And to the right of the line of no effect, these analyses found there to be a positive relationship between grass cover and eucalyptus seedling success. Similarly to the blue tit data set, there's substantial variability in the direction of effects, with most finding there to be a negative effect of grass cover on seedling success, and about a third finding a positive effect. However, most effect sizes were extremely small, with a meta-analytic mean of about -0.09, suggesting an extremely small or null true effect. There's also huge variability in the magnitude of effect sizes, varying from above 0 to like less than -4, shown by this outlier to the left of the plot here. So for the full data set, nearly all of the heterogeneity is due to between study variation, with I-squared coming in at about 98.6%, less than 2% of that heterogeneity caused by sampling error. But when we remove some of the outliers, those strongly negative outliers, I-squared drops to only about 65%, which, although this is less than the average meta-analytic mean across meta-analyses in ecology, is still very high, considering that these are all analyses of a single data set. But for the blue tip data set, there was no substantial difference observed in I-squared when we removed outliers. So this suggests that variation in effect sizes is driven much less by analytic variation than sampling error for the eucalyptus data set than the blue tip data set when outliers are removed. Okay, so hold on. A prominent statistician and meta-scientist tweeted recently, I really don't like the ManyAnalysts type papers. They make it seem there's a problem where there is none. Sure, you give a bunch of random people with no expertise an incredibly vague research question and the p-values of their tests differ. Who cares? So, you know, although the tone of this tweet is perhaps a bit harsh and, in my opinion, downplays the degree of thought and rigor that goes into conducting ManyAnalyst studies, and although we arguably did provide a well-defined research question and crowdsourced analyst, you know, with at least some degree of proficiency in ecology and evolutionary biology and competence and in statistics, there's certainly a valid point here to be made about the quality of the analyses. What if there's just, you know, a bunch of junk analyses in here creating a whole bunch of noise? Well, since each of the analyses was peer-reviewed multiple times, we tried to separate the wheat from the chaff, so to speak. So does the effect of analytical heterogeneity on the variation in results change when poorly peer-rated analyses are removed? So to answer this question, we looked at the influence of peer review on patterns of heterogeneity by rerunning the meta-analysis first, by removing analyses with at least one unpublishable rating, and secondly, by also removing analyses with at least one rating of publishable, but with major revisions. So for the blue tip meta-analysis, there was no real change in I-squared or the proportion of variation attributable to analytic heterogeneity versus sampling error, nor was there any major shift in the meta-analytic mean effect size. However, for the eucalyptus analyses, we see a really large drop in I-squared when those poorly rated analyses are removed. And we also see a shift in the meta-analytic mean effect size, as well as a decrease in uncertainty about those estimates as well. So what's going on here? So, you know, trying to break it down, we ran the meta-analysis with a fixed effect for publishability, and there's no real difference between each of those groups of effect sizes as a function of their peer review rating. And then we thought, okay, well, you know, you can have two distributions that are very different, but they still have the same central tendency. So we also, this is a pre-registered model, we looked at how the peer review rating affected the deviation from the meta-analytic mean. And again, there was no real influence of peer rating. So the only kind of conclusion I can draw here is that poorly rated analyses are just strongly driving that proportion of overall analytic heterogeneity. So what's going on here? How do we interpret these patterns of variability, and how do researchers' analytical decisions influence these patterns? As this figure here illustrates, throughout the course of analysis, researchers make numerous decisions from beginning to end, choices about how to operationalize the response variable, the independent variable, what model to fit, what metrics to use for model selection, and so on and so forth. And all of these choices influence the final analysis specification or strategy. And this analytic decision graph is just one realization of a specification for a particular modeling study. So when we consider the collection of these analysis specifications for each of the EcoEvo data sets, are there any particular decision points or choices at these decision points that are particularly influential on heterogeneity? And I'm afraid I don't have a nice, neat story to explain these patterns of variability that we observe. So let's just wade through the mess together. So for the blue tip data set in this top panel, we have here the same forest plot as I showed you earlier, but it's tipped on its side. And in the bottom panel, we have different decision choices or specifications plotted for the corresponding analysis in the top panel. I've only shown a couple of decision points here that were painstakingly coded by Hannah and Tim. And in the first collection of points, we have the predictor variables. In the second collection beneath that, we have the response variables, and the bottom two lines there represent the model type used by the analysts. The main message that I want to convey here is that there's a hell of a lot of heterogeneity in analysis specifications, and to me at least, there's no clear-cut pattern in how those analytic decisions influence analyst results. And the same is true for the eucalyptus analyses, with particular decision realization spanning the range of effect sizes put forward by all of the analysts. So for the EcoEvo data sets, as Hannah mentioned earlier, we ran a bunch of different models looking at the effect of particular analysis decisions or properties of the analyses, like uniqueness of variables. And we basically found there to be a weak or no influence of these attributes on the effect sizes. And these patterns changed depending on whether outliers were included or not, and were different between the eucalyptus and blue tip data sets, but not in any explainable or understandable way. What we can explain, however, are the effect of outliers on effect sizes. So for the blue tip analyses, outliers occurred due to highly correlated predictor variables. Surprisingly, both the highest and the smallest effect sizes came from the same analyst with the same model. The only difference being the response variable was different. All other covariates for both of the models were the same. So then how do we see such a wild reversing of the direction of effect and a dramatic change in the magnitude of effect then? Well, when we explore the correlations between the variables in the raw data set that the analysts were examining, we see that there are at least three highly correlated variables here, shown by the red squares. In particular, brood size at the start of nestling period and brood size at day 14 of the nestling period, with a correlation of 0.9, which, logically makes sense. So in one case, this created an unexpected sign, since presumably the focal variable was just explaining some residual variation after the other soaked it up. In the other case, the sign was okay, but the value was extreme, probably because the other highly correlated predictor was explaining some of the residual variance and therefore making the primary effect appear stronger. Interestingly, unlike for the eucalyptus analyses, dropping these outliers didn't significantly reduce the I-squared value. So for the eucalyptus data set, all negative outliers are based on extremely small subsets of the data set and highly aggregated versions of the data set. So with one analysis, they had only 18 observations, and in that case, they just aggregated across all 18 sites, discarding a lot of information. And in the other cases, the sample size was less than half of the mean sample size across all of the analyses. So to wrap up, I'll just briefly discuss the variation in results between the two data sets and summarize some general patterns. So both analyses of the blue tip and eucalyptus data sets demonstrated large heterogeneity in effect sizes, and this was primarily driven by analytic heterogeneity rather than variation due to sampling error. But variation in effect sizes for the blue tip data set was influenced much more by between study variation than was observed in analyses of the eucalyptus data set when extreme outliers were excluded. And for the unfavorable review ratings, it seems that these analyses disproportionately contributed to the proportion of analytic heterogeneity driving overall heterogeneity in effect sizes. Finally, univariate methods don't really reveal strong effects of particular decision points or decision choices on the results. So why did we observe these differences in analyses of each of these data sets? Why was there much less variability in eucalyptus effect sizes than blue tit effect sizes when outliers were excluded? These differences could be driven by differences in analytic strategies or by differences in the analysis data sets themselves. So possibly there are true biological differences in these systems, or by some interaction between these two things. In terms of differences in analytic strategies, maybe there were just more opportunities for different hierarchical models in the blue tit analyses. There are many different aspects of the study that were manipulated, and therefore many different permutations of random effects that analysts could use. There are different types of parents, from genetic to foster to social parents. The analysts could include random effects for year, for nest, for area. And then there are differences in analysis data sets or true biological differences in effects between these data sets. So perhaps there are just more covariates with larger effects in the blue tit data set. So by including or excluding covariates with large effects, this moves the effect size around more. Perhaps there's just a larger overall biological effect in the blue tit data set compared to the eucalyptus data set. So with a smaller effect, as well as perhaps less covariates, with a strong effect on the response variable, it's less likely that the analysts are going to be able to recover this effect. And this is something that I observed when I was going through the eucalyptus analyses, was that only those analyses that included a particular set of covariates and particular moderator variables were able to identify a plausible but complex mechanism for grass cover positively influencing eucalyptus seedling growth. All right, now I'll hand it over to Tim Parker, who will discuss the implications and some potential solutions to this analytic heterogeneity.
Okay. I guess slides must have moved from the other folder because I updated this. But anyway, before I get started, I just want to call attention to the fact that besides Elliot and Hannah and myself, there are a bunch of other co-authors on this. There are a few other, so Shinichi Nakagawa is, along with Elliot, Hannah, and I, has been sort of a core organizer of this project. Simon Griffith, Pete Vesk, and Fiona Fiddler are also original organizers of it. And then that XXX additional analysts and reviewers, I updated this yesterday, and it was, I think it's about, it's about 250 other people who contributed to this, and they're all going to be co-authors on this work as well. Okay, so we just heard those talks 1 and 2 from Hannah and Elliot, and now you're going to hear from me. Just sort of the implications for these results, the implications of these results that Elliot was just talking about. So this is what Elliot just showed us. We've got substantial heterogeneity here from both data sets. They look a little bit different. That heterogeneity looks a little bit different in these two data sets, which, as Elliot pointed out, I think is really interesting. But nonetheless, there is substantial heterogeneity that in either one of these data sets, I think, has important implications. So what I'm going to do today is briefly go over probably some overlap, some of the points that Elliot just made about potential causes of this heterogeneity. I'm going to discuss with, again, probably some overlap with what Hannah was talking about of why heterogeneity in results might be a problem. And then I'm going to talk, spend most of the talk talking about potential analytical responses to the knowledge of this heterogeneity. So we know there's this heterogeneity. What the heck should we be doing about it? So, okay. So as Elliot just pointed out, there's quite a number of potential answers as to why there's heterogeneity. Elliot was talking about the differences between these data sets as to why there might be differences in heterogeneity between these two sets of analyses. Many of the explanations that Elliot just gave also can just apply in general to, why do we have heterogeneity? So folks might be analyzing different subsets of data. They might be including or excluding different covariates, especially ones with large effect. There might be differences in model structure, which there was a lot of. I went through the code for everybody who submitted code. And by the way, not everyone actually submitted their code, but everybody who submitted their code, I went and looked at all of those models and coded all those models. And it's fascinating. I mean, we haven't actually tried to quantify this per se, but I would, with a pretty high degree of confidence, say that nobody did identical analysis to anybody else. Everybody did something different than everybody else, and which is pretty impressive. People selected people can select different response variables. Selection of different primary independent variables. So with the blue tits, there were lots of options for how you could do this. Some people looked at actually number of siblings. Some people used whether the number of siblings had been experimentally categorical predictors, whether the number of siblings had been experimentally increased or experimentally decreased, for instance. So lots of different things to do there. I want to call attention to the fact that so this is something that I think both Hannah and Elliot alluded to. A lot of this stuff could be and has been criticized previously as just essentially an insufficiently specific question in a ManyAnalysts project. So this is a paper that was published in response to the original Silverzahn et al. Red card paper, and these folks claim that the problem with the red card paper, all it did, the big problem was that just the meta-analysts hadn't specified a narrow enough research question. And my response to that is the question that certainly the questions that we posed in our that we presented to the analysts were exactly the sorts of questions that researchers ask themselves. If you look at meta-analyses in ecology and evolutionary biology, they're exactly the sorts of questions that people pose in a meta-analysis when they go to bring all sorts of research together in a synthesis. So I feel quite confident that what we've included here is an actual representation of the way ecologists and evolutionary biologists ask their questions. Okay, so it may be probably, I think it is relatively obvious as to why this heterogeneity in outcomes is a problem, but I'm going to take a moment to talk about it. I think, quite obviously, when individual results replicate poorly, that's an issue. Like if you go to the literature and you find a result, and you know that if somebody else had done the analysis, the result could be quite a bit different. That's not good. You want to have confidence when you go to a paper and you read a result. You want to have some sense that it's reliable and replicable and repeatable. So this alone, I think, is reason to be greatly concerned by outcomes of ManyAnalysts studies like this. But as Hannah talked about, there's also substantial opportunity for bias to skew reported results when we know that not various model specifications can create quite different results. It means there's a heck of a lot of opportunity for various forms of p-hacking. It's not hard for somebody to just change their model specification, get a different result, and say like, "Ooh, I like this result better. This is the one I'm going to submit." So we might not actually, in the literature, it might not be a random draw from these various outcomes. It might be a really biased draw that could then mean that even if we average across many of them, we're not going to get a reliable average. So, and I've got a couple of graphs here from that same paper that Hannah was mentioning before, just showing these high. This is the prevalence of prevalence of folks who failed to report a non-significant result. So this is more than 50% of ecologists and evolutionary biologists, admitting to this sort of cherry picking. This is what Hannah was talking about before. Here's another similar one. Here's non-significant covariates not reported, or some models not reported. So, ecologists admit that they do this, and combine this acknowledgement that we do this with the fact that it's easy to get a lot of different results from the same data set. It's concerning. Okay, so what I really want to talk about is actually what I think is the really, really hard question to answer, which is what the heck do we do now that we know that results can be so variable? How do we regain confidence in our results? So I'm just going to go. So I'm going to go through and talk about some things that are out there that people do, and some of these. So robustness checks are probably familiar to many of you. In some disciplines, they're quite common. I'm obviously an ecologist. I'm not an economist, but thanks to the Replicats projects, I've read a fair number of economics papers in the last couple of years. And I know that this is a relatively common thing, and certainly in some realms of economics. Some ecologists do this as well, although it's much less common. And this just involves, so a robustness check usually just involves, some sort of additional analysis, often just one additional analysis, maybe several additional analyses where you say like, oh, we've analyzed this in several different ways, and what do you know? We get similar results. So in practice, from what I've seen, and other people with more people in disciplines where robustness checks are more common may wish to disagree with me, in which case that's great. But what I've seen is it typically looks like robustness checks are presented to confirm the reliability of results you're showing. So somebody isn't going to do a robustness check, find something different and say, oh, I don't know, this one said this thing, this one said another. Usually the results of robustness checks are at least relatively consistent. And of course, if you have many, many different options for different ways to do your robustness check, probably means you got a lot of options for finding similarity. So some limitations to robustness checks, if you just are doing, one or two additional analyses, you're not really sampling from this sort of distribution that we've got here, and you might not really be assessing the robustness of your analysis. And then, of course, as I just alluded to a moment ago, there's a risk of bias here. So if you've got a lot of different options for which robustness check you're going to present, you can still just sort of, cherry pick several robustness checks, several different analyses that show pretty consistent results. So you could get around that potentially with pre-registration or with registered reports. So some other ideas that are floating around out there kind of in response to this. So these are all coming out of social science. So multiverse analysis, which was originally kind of narrowly defined as just performing the analysis of interest across the whole set of data sets that arise from different reasonable choices from data processing. So this is just about which data you select. Which is obviously just sort of one component of the variability available to analysts. So just analyze a bunch of different data sets. So limitations here, defining the scope of reasonable here is interesting, and the number of potential analyses can get quite large quite quickly. So the scope of what's reasonable is subjective. We can move on to specification curves, which are conceptually, really just an expansion of that narrowly defined metaverse analysis. Here, we're not with the specification curve. You're not just looking at a bunch of different choices of data sets. You're also looking at choices of model specification. So you a whole lot of different stuff. So really just a more general version of the metaverse. Here from this original specification curve paper, this is a graph showing the let's see, what do I want to say about this? So this was that original paper, specification curve paper, looked at data, or looked at models from a paper that had made the the claim, which seems to me to not be a particularly plausible claim. But the original paper claimed that people take fewer safety precautions and thus die at a higher rate when hurricanes are given female names. So these folks, the folks doing the specification curve analysis chose a few different options for varying the specification curve, here, which are, there's different variables there on the left-hand side, and you can see the little dots going across the curve there just shows, which various specifications occur in each model. So then there's 300 different specifications or different models here, and then the curve at the top just shows the number of extra deaths predicted if the hurricane name is female. And what you can see at the top there is that just 37 of that's specification. Anyway, it's just 37 of 1,728 specifications led to statistically significant, p smaller than 0.05 sorts of answers. So, which at the very least suggests, it's a very narrow set of specifications that could have led to that conclusion. What's more interesting is when you take those different specifications and you do some sort of randomization, like you create a null distribution of specification curves. In this case, by just randomly assigning male or female names to each hurricane, you do that over and over again, and this is what you get in this case, which is the blue line, or the observed data, and you see these different 1,728 different specifications, and that basically the observed data follow the random data pretty much right on almost perfectly, which makes us in this case pretty convinced that there really isn't a relationship between number of people who die from a hurricane and the gender of the assigned name. We can get other sorts of results from a specification curve analysis. So here's one based on a study where fictitious names were used to apply for real jobs, and the names, this was in the United States, the names were stereotypically ethnically Black or white, and what we see here is that the specifications, range of specifications with the real data in blue is well outside the realm of random. And so in this case, we're quite confident that the people who are offering jobs to these candidates are influenced by their perception of race. So racism is real. Okay, so specification curves are potentially really powerful, but there's limitations are basically the same as the limitations with the multiverse. Depending on the scope of what's theoretically justifiable, we can very quickly end up with millions of potential ways to specify. And we can Simonson et al. Recommend is you know, a random draw from that set of possible specifications. Again, even just determining what that theoretically justified scope is going to be subjective. And I'm going to say some more about some limitations of that in a minute. I want to mention, well, a couple of other things here. I want to mention model averaging, because model averaging is something that's become, in certain subfields of ecology, is really quite common and has been widely embraced. And this is where the analyst comes up with a set of alternative models, usually a relatively, Burnham and Anderson are the authors who strongly advocated this, and their work is associated, their names are usually associated with model averaging in ecology. They advocate for taking a very small number of alternative models and averaging across them typically based on AIC weights. And so Burnham and Anderson recommend using 20 or fewer models with strong a priori justification. So obviously that's far fewer than in, say, the specification curve, and again may not really represent the scope of what's possible, especially if you're you know, choosing a kind of a narrow set of so-called plausible models. Again, you know, there's a high opportunity for subjectivity here. So for all of these, for the metaverse, the specification curve, or for model averaging, you know, there's some important things to consider. With greater than you know, approximately like 35 variables in each of our predictor variables in each of our models, obviously there's a lot of conceivable specifications, and conducting analyses that really thoroughly explore that analytical space of millions of potential specifications, it's going to be challenging. You know, I'm sure there are some of you in this room who think, oh, that's not particularly challenging to me. For me, it would be very challenging. It's probably beyond the skill and resources of what many analysts working in ecology and evolutionary biology are currently up for. You know, if you just told somebody to do this right now, most ecologists and evolutionary biologists would not be able to do this, which isn't to say they couldn't learn to do it. But I think that's a substantial limitation. And so and I'm just listing a few sort of potential responses to this to this recognized heterogeneity. But this last one that I'm going to mention is really just, you know, express caution and humility in interpretation of results. You know, we tend to want to write papers that suggest we've drawn the conclusion available from our data set, and maybe we should just stop doing that. Maybe we should just say, I don't know, here are the results I've got. Maybe they're right, maybe they're wrong. I personally don't think this is very likely to happen, because I think incentives work pretty strongly against it. And the fact of the matter is, all it does is acknowledge our uncertainty. It doesn't really get to the bottom of it in any way. So we're still left with that uncertainty. So I think the way forward is unclear. I don't know what ecologists and evolutionary biologists are going to do about this. They haven't seen this paper yet. So I've talked to I've given this seminar a few different departments, and interestingly, people have not so far been really particularly interested in talking about the way forward. They're more interested in, like, well, what's the difference between blue tits and eucalyptus? Anyway, maybe you guys are going to have some more interesting things to say. Anyway, I think specification curves are wonderful if they can be managed. I think pre-registered robustness checks may be more realistic for many of us. I think there might be other solutions that are even better that I haven't talked about. And I'm looking forward to ongoing discussion, hopefully today and in coming months and years, about what do we do about this variability. So I'd like to invite Elliot and Hannah to come up, and we'd be happy to take your questions. Okay. Oh, there's two Patricks in line. I'll go Patrick.
Happy to be the first Patrick. Yeah, I mean, really impressive set of work, and it sounds like a huge challenge to manage. Having worked on some of these big team types of projects, I've been there. So well done, first of all. I felt like both you, Tim, and Elliot sort of dismissed the idea a little bit of framing questions narrowly as a solution. I guess I want to challenge you on that a little bit. So first, I guess the first part of my question is there anything about the substance of ecology or evolutionary biology that you feel makes it hard to pose the questions narrowly? Is there a limitation there, something inherent to the subject matter? And two, do you see any obstacles, either social or substantive, that would make it hard to phrase greater questions through?
I'm happy to answer that, but okay, yeah. So I mean, so some of it is, I think, as I said when I talked about this, I do think there is this social phenomenon. It is sort of how people answer the questions. Whether it has to be that way, I think, is a really interesting question. I think how do I want to? I'm not exactly sure how I want to answer that question. I think that when you look at how ecologists operate, and what the type of, how the different systems that they're working in. So for instance, if we look at meta-analyses in ecology, they're almost always, bringing together work that's been done in different systems. So sometimes they're meta-analyses where people are focusing on an individual species, in which case, maybe in that case, there's room for really quite narrow definitions of questions. But much more typically, I'm studying this question in this species of bird, and somebody else is studying it in that species of bird. And we all think we get together, we all want to know the same thing. We want to know, about, I don't know, as the answer was, the question here was, how does sibling competition influence growth or something like that? Something we all want to know. We don't have any particular reason to want to, define growth in some particularly narrow way. We don't have any a priori reason to think like, well, this is the right way to define growth, and that's not the right way, or this is, so I do think that there are real reasons why people are asking these vague questions, because they're asking the question sort of at the level of the underlying theory.
I think it's also a factor of if you ask a really specific question, you have to write a really specific paper, and then you're writing a really specific paper for a less high impact journal, and there's pressures there. I'm not saying that that's ideal. I think you do find some specifically identified hypotheses in more applied research where they want to ask a specific question about a specific context because they want to do something to answer that. But I think it can be done. It just means that you're asking something very narrow, which isn't of interest to many people, and that's problematic in publishing.
Okay, I'll go with Patrick number 2, and then I'll let somebody else follow.
All right. Yeah, firstly, thanks so much for the presentation. I thought it was totally fascinating and really important in ecology and my question is, so you have this question of whether competition among siblings affect growth. And suppose there's reason to believe that there's a non-linear effect. So it doesn't matter whether you have 1 or 2 siblings, but it may matter a lot when you have 3, 4, 5, 6, 7. It seems to me that this sort of pattern would maybe plausible, depending on the ecologist, not be summarized by a single. How do I fit it into the analytic frame?
Yeah, so I think that's absolutely plausibly true. Like that there can, that there might not be. In part, that's one of the reasons that some analysts submitted more than one answer to the question. So because, for instance, so we had if you use the experimental data, you could look at net broods that had been manipulated to be smaller, those that have been manipulated to be larger, and those that were unmanipulated. And so the difference between unmanipulated and those that had been manipulated to be smaller, that was a different difference than those then manipulated to be larger versus not manipulated at all, because essentially you're correct that, there are the difference, that, well, increasing a brood has a different sort of effect than decreasing the brood. And so, yeah, I think that is a potential issue. And I don't have much to say about it other than, sometimes they're nonlinear effects and people aren't paying attention to them, and sometimes they are.
I think part of the reason, so that's part of the reason we, which we didn't discuss too much in this talk, is that we looked at the effect size estimate, which doesn't take that into account. And we also got people to use their model to predict to 3 pre-specified scenarios. So there's like a low scenario, a middle scenario, and a high scenario, which should capture if there are nonlinear effects going on. But it was really hard for people to do. So there's some additional difficulties in, we'll have to lose a bunch of data because people were unable to follow our instructions.
And by low, medium, and high, you mean the number.
Yeah, I mean, we just, for every potential predictor variable, we had like sort of 25th percentile-ish, 75th percentile-ish, or median. And so we had like, you choose whatever, however whatever. Yes, so the short answer is yeah. So when there's this many siblings, what's growth going to be like? Yeah, and so in those results, as Hannah said, we have fewer numbers from that because we were less successful at getting those data from people, but the results are pretty similar. Somebody else choose.
I think Bob had his hand up for a bit.
First of all, just totally brilliant presentation from all 3 of you. Can't say not wonderful things about it. Just a 2-part question. The first one is, if you had to find the answer to your question, given the data you have, wouldn't the most, how do you feel about simply doing meta-analysis on all the estimates? Would that be what you think? Would that give you the right answer?
I'm less and less convinced that there is a right answer.
Right.
I'm not certain that there is a right answer to the question.
Best answer.
Best answer. That would give you a very good answer, I think. Yes. I think I would try to look through, so people also provided their written answer, and I think I'd read through all of those and see on balance which direction they were going in. I think we did code them up. I don't know that we've actually analyzed that yet. I think I'd look through them and see, I'd do a vote count.
I think that's an interesting question to ask, given all the data, if you had to choose the answer. Because you don't have publication bias.
Yeah.
So how would you get that? My second question is, you didn't mention automatic model. Do you think there's much of a role there moving forward? Where
You mean like stepwise?
reduce the amount of choice people have, push a button, let the mathematics take over.
You're talking like a stepwise procedure, or there's like an AIC ranking?
Like that, or
Sorry.
like lasso or something.
Okay.
Sorry, like for us to then analyze like the collection of analyses that people put forward, or do you mean as a solution to
You got a particular coefficient or set of coefficients you're really interested in.
Yeah.
You've got a lot of, control variables, and you can specify them in any way. And so there's a million ways of doing that. So you have some things models that
I don't think that's a good solution. Also, it's like that's what most of the ecology data set analysts did anyway, and I think it's really sensitive to the set of candidate models that you throw at it. And then also there are like well-known problems, especially in ecology, if you're just like dumping a whole bunch of variables in, and then you get some supposedly best model from that. There's a chance that you just it's just a spurious finding. I think it's yeah, you can get some really dodgy results from that. There's one example where they had these species distribution maps, and then they threw a bunch of like paintings as like the underlying data, and then the best model picked from that chose like the paintings as the best, like you could get the paintings out of it, and there's just, unless you're picking, throwing biologically plausible models at it with I don't think AIC or model selection is necessarily the solution.
I push back a little bit now, but I'm gonna be quiet a little bit about the question. The researchers in both the many-analysis studies and the survey were self-selected, is that correct?
Yes.
And did you try and adjust that, like look at what the characteristics were of the journal, the paper that had been published in the journal said no, and said no, I won't, or didn't participate, the 15% responded with a different population in any measurable way from the 85% who didn't.
Oh, you're talking about the survey?
Survey, in most cases, it's self-selecting.
Yeah.
My intuition is that the problem works because the people who volunteer to take part in this have more of a sense that they should, that this is an important question, these methodological questions matter, and we should all be trying to do our best.
Yeah.
That's why they're participating in the study. So if you were able to force people to participate, you get even more alarming results about the variance.
That's
That's a very interesting question. I'm not sure. I think, given that there's such a wishy-washy relationship between the quality of people's analyses and their results, I have a feeling that it wouldn't be that much different if you had people who are less excited. I think they just try slightly less hard and do a basic thing. They'll probably find a middling result, but I obviously have no idea.
Rachel.
We haven't yet. It would be a little bit complicated because people participated in a team. So then we'd have to make a judgment about, is it sufficient to have one experienced person on a team? What if you have 15 people on your team, theoretically, who are all not that experienced, but they all got complementary experience? I don't know. I think, yeah, we have to make some arbitrary judgments about expertise, but we could have a look in that space. Do you have any thoughts about it, Elliot?
Just that, yeah, I don't know how much of a difference it might make. Just thinking back to, yeah, like that graph when we looked at the mean effect sizes across different peer review ratings, like even the unpublishable results, like weren't actually that different. And then when we looked at deviation, same thing. It was only when we dropped them out that it was just this I-squared value that changed. And is that meaningful in terms of the actual result? Yeah. Yeah.
That's definitely true.
Yeah, I mean, I think the argument again, the biggest, if I were to say, well, what's the biggest problem with this? I think the biggest problem is that, yeah, the people who were analyzing the eucalyptus data set didn't necessarily know anything really about eucalyptus. The people who were analyzing the blue tit data set didn't really necessarily know anything about blue tits. So I think that that's a potential, hypothetically, a potential problem. I don't, having looked at the model specifications and looked at a lot of these models, I don't really think that it, you know, I'm not sure like what you would have really wanted to know about blue tits, for instance, that would have really influenced, because we gave people a bunch of information about the study, and there wasn't, you know, they were both pretty simple questions with that I don't think required necessarily a lot of sophistication or a lot of background knowledge to do a reasonable analysis. So that's my opinion. And also just editorialize, having looked at a lot of these analyses. I mean, I was often most often I was impressed with these analyses. I can't tell you how many, well, and the number of times I was like, ooh, that's really cool. And I'm like, ooh, I could use that R code myself. Like, this is really neat stuff. So, and a lot of those people were junior people. And certainly in ecology, I think there's actually a relationship where by like the average junior person is more analytically sophisticated than the average senior person. Yeah. Yeah, I mean, so that's something we don't actually, well, we can, that's one of many things that's not really, it's not in our registered report that, there's a whole, as I don't know, one of you two alluded, there's like a lot of stuff we'd like to continue to do with this in the future, but we need to get the registered report done first. Yeah.
They did, yes. Well, I mean, obviously not for everything, because I guess we didn't have a very good understanding of exactly what decisions they'd be facing, because they were doing models differently, but we definitely asked them to justify their model choice. The variable choice, and describe what modeling type they used and why it's appropriate in that circumstance. Did we ask them for anything else? Do you remember? So yeah, so we asked for those two things, and then they had to write up their methods like you would for a paper. So there's non-zero justification there as well.
But I would say there's really kind of often an unsatisfying amount of information in that realm.
How about intermediate step, worry about data analysis, get more spectral diagram. You have discussion there. Use that.
Yeah, while we were, sorry.
No, go please.
While I was listening to Tim speaking, I was actually thinking that could be a really great way of a way forward. Like, without actually having to get people to analyze the data, you could talk it through with a bunch of people who are also expert in the area, but maybe have a slightly different statistical background, get them tools or other cause a model, come together, and then move forward from there to try and get to a more parsimonious, but like a good result. I think that could be a good way forward. I think I've not answered your question because I got so excited about that. What was the question again? Sorry.
Well, I suggest, I think what people have been talking about, the almost the opposite how expert are they? Everybody puts them forward by themselves. Before it does that, before that's all the time. There might be one group of them. They're not made up of 20. And they look it down, before people get to the numbers.
So I want to, so the blue tit data set actually was a data set that I helped gather when I was doing a postdoc, 20 years ago almost. And I had done a variety, I mean, I published some things off of the data set, but I had done a variety of work with it, and had actually wrote a manuscript based on those data prior to us doing this. The manuscript, in the manuscript, what's the concise thing to say here? Basically, some people had written some other studies with done some other studies with this same species, looking at basically that question. And so I wanted to write kind of a meta-sciencey paper where I did a bunch of different replications. I'm like, well, what if I replicate this way? Or what if I use decisions and replicate this other way? Or what if I just design the study the way I think it should be designed? And one of the things that became really clear to me doing that is that the number of, and that paper was rejected twice because people didn't like my framing, and then we used the data set here. But I'm overwhelmed by the number of plausible specifications. Like your suggestion doesn't, like for me, there were very few analyses that I saw people submit where I just thought, well, that's dumb. That wouldn't work that way. Like, I mean, I can imagine causal pathways, many different causal pathways through these data. That's my perspective on it. Yeah, I find it sort of overwhelming. And actually now I often kind of find it when I'm publishing a paper trying to decide what analysis I'm going to do, I loathe that because I find so many different alternatives plausible, and I hate to make those decisions. That's my perspective. So,
2 more questions and 2 minutes
Oh,
left.
yeah, sorry, I'm looking, yeah, go for it. Matt.
I should have said it.
Yeah, yeah.
Excellent work. I was wondering if you've looked at it yet, how much inter-rater agreement there was between the peer reviewers of the analyses, and why you chose 5, and as someone planning to do a study like this in future, whether I need to get 5 people to do it, or are they all pretty much saying the same thing?
I haven't like quantitatively looked at that. But yeah, there was a lot of variation, especially in the categorical ratings as well.
You've done a many analysts and many reviewers.
In terms of Wi-Fi, I'm pretty sure that was decided, it might have, I don't know, my post-hoc memory of how that was decided was what we thought was plausible in terms of recruits. So how many people we thought we'd be able to get to review, and then how we distribute them. Because we thought that, I think it's a reasonably arbitrary, we thought we'd ask each person to review 5 things. So if we had a similar number of reviewers to analysts, we'd get 5 reviews of each analysis. I think that was how that went down. If you are thinking of doing something similar, you could have a look at our variation in reviews, and I'm sure there's some kind of a power analysis you could do to work out the answer, isn't it? Pretty good.
Last question.
Jenny?
I was wondering whether you thought about how this methodology can be adapted for situations where you need to get an answer about kind of variability, very urgent, like testing over time. Not as flying that what you're saying does not have any it's kind of important.
Well, I think there's a lot, I don't know. I mean, yeah, maybe my co-authors have more to say about this than I do, but I mean, one of the things we learned is that we were fairly poor at anticipating all the different things that the analysts might do. And that we thought we were being thorough, and it turned out we were not being thorough in trying to anticipate, what sort of responses people would give us. And that's one of the reasons why we're still working on this. Eddie?
I think I need to think very deeply about this question, but I don't know that I've got an answer now. I think, as Patrick was suggesting, having a narrow question would be a really important starting point, particularly when it's urgent. That's going to be easier as well, and might make it easier to compare people's analyses.
Just from a computational perspective, I think you'd want to have the computational infrastructure set up ready to go, because trying to extract all of the data from the submitted analyses, or even just from the Qualtrics surveys, has been an absolute nightmare. So you'd want that ready to go, and then you could just feed your data into that. But again, I agree with Hannah. You'd want to have, I think, a narrower question ready for rapid decision making based on that data.
Thank you very much. Our time is up. It was so interesting, and I was so happy to see the results because I was one of the participants.
Yeah.
So it was excellent. All the talks and the discussion. Thank you very much.
Thank you.
And